In stoichiometry, when there are reactions with two reactants, we can calculate one to be the limiting reactant, the one that runs out first, and an excess reactant, usually one that there is plenty of so that the reaction completes all the way. When we did our initial exploration, we made s'mores. Chocolate was our limiting reactant because the chocolate ran out first, and we had excess marshmallows and graham crackers. The same concept applies to chemical reactions. The steps for determining the limiting and excess reactants are to start with a balanced chemical equation. This is critical. Without a balanced equation, the math will not work out. Identify both given quantities. We'll be solving two stoichiometry problems. For both of these, we choose the same product to be the endpoint. The larger answer will point then to the excess reactant, and the smaller answer will indicate the limiting reactant. Remember, the answer for limiting an excess reactant has to be a reactant from the equation. Let's do a sample problem. This says that methanol, CH3OH, is the simplest of the alcohols. It is synthesized by the reaction of hydrogen and carbon monoxide. Here's the formula that's already been balanced. CO plus 2H2 yield CH3OH. The given quantities are 500 moles of CO and 750 moles of H2. We will solve both of those using stoichiometry to the same product, CH3OH, and determine which is the limiting reactant. Once you've done the math, it's important to remember that carbon monoxide and hydrogen gas are the reactants. Those are what we're choosing from. CH3OH can't be the answer because that is the product. We need to start by writing down both given amounts, the given for each reactant. We need to fill in the units in advance, knowing that they need to cross-cancel in this mole-mole conversion. Next, we need to put moles of product in both brackets, since that's the answer we're seeking. Finally, we'll actually fill in the numbers based on the coefficients from the equation. There's 1 mole of carbon monoxide, there's 1 mole of product, and there are 2 moles of the hydrogen gas. Multiply across the top, divide across the bottom. That amount of carbon monoxide will yield 500 moles of product. The 750 moles of hydrogen as reactant will yield us 375 moles of product. Therefore, carbon monoxide is our excess reactant. Our limiting reactant is going to be the hydrogen gas. Here's another example. In this reaction, the synthesis of aluminum and oxygen to create aluminum oxide, you have to balance the equation. You need to make sure that you can identify your reactants of aluminum and oxygen and identify your product of Al2O3. These coefficients will be useful in creating the mole ratio. All right, a little bit of practice balancing equations. We can see in this example that there is a 2-3 disagreement with our oxygens. So we begin by swapping and putting a 3 and a 2 so that there are 6 oxygen on both sides. This creates a situation where there are 4 aluminum to the right, so we make 4 aluminum to the left. Our given information is 6.50 grams of aluminum and 4.23 grams of oxygen. So we'll write that down as our given information to begin. Here's our given information. The next step will be to put the molar mass of each reactant. You can see in step 2 that we have looked up the mass from the periodic table of 1 mole of each substance. Step 3 is to do the mole-mole ratio using the coefficients from the equation. We set it up so that our units will cross-cancel. On the top of our mole ratios, we'll put the moles for the substance desired, in this case, the product, Al2O3. The numbers we need will come from the balanced chemical formula. And the final step is to do the molar mass of the product, aluminum oxide. We'll multiply across the top, divide across the bottom to come up with the two answers. While 6.50 grams of aluminum will yield 12.3 grams of product, the 4.23 grams of oxygen only yields 8.9 grams of product. Therefore, aluminum is our excess reactant, and our limiting reactant is the oxygen in this example. I hope that helps you with limiting reactant problems.